Welcome back to this lecture series on concurrency, state models, and design patterns. Today we're going to have a look at fairness and optimism, and in particular, a class of problems known as readers and writers. First of all, we'll review the definitions of fairness and have a look at what different ways fairness can be defined and how priority plays a role. Then we're going to have a look at this readers and writers problem, and we'll see how by distinguishing clients that perform only read actions from write actions, we can increase the amount of concurrency and liveness in our code. And we'll see that there are different kinds of policies we can put into place with different impacts on fairness. Finally, we're going to have a look at a rather different approach to synchronization, which so far has been pessimistic by means of using locks, and we'll look at how optimism can also provide us a little bit more liveness at the risk of having to roll back certain actions. First, we'll have a look at the definition of fairness and the role of priority in fairness in the context of having methods concurrently available. So the basic pattern, the design pattern we're looking at today, is that of allowing methods that do not interfere with each other to be made available concurrently. So we will implement policies which can enable and disable methods, so to have guard conditions that will control when certain methods can be executed and when they cannot, based on the state and of the object, the state of the threads that are currently in there, and which kinds of methods we want to run. This can be quite interesting in various situations, in particular if the host objects are accessed by many different threads and the host services are not completely interdependent. So for example, you don't need to perform all the methods under complete mutual exclusion. The design pattern makes sense if you need to improve throughput for some methods by eliminating non-essential blocking. Note that you don't want to do this always because, like with most design patterns, you're going to be making your design more complex. And this additional complexity makes it harder to reason about your code and makes the code harder to maintain. However, if you do have a situation where there are lots of threads trying to access certain objects, and you do have this possibility of playing with the locking policies, then you may have a significant win. You also want to prevent various accidental or malicious starvation due to some client forever holding its lock. So we can see that starvation becomes an important issue as well. On the contrary, if you fully synchronize your host object, then this is going to lead to deadlock or possibly other liveness problems. So this is a situation where you want to relax the full synchronization by having some methods available concurrently. So how do you proceed? You need to somehow layer the currency control policy over the underlying mechanisms by introducing a policy definition. So under what circumstances do methods run concurrently? You need to perform some instrumentation, that is, you need to keep track of the state of the object and the state of the threads that are currently in there. So this is additional state variables to instrument, track the state of the object and its clients. And you need a form of interception. So the host object intercepts the public methods and relays them to protected methods that actually perform the work. So you want to separate a layer of policy over the underlying methods that are providing these services. Now let's have a look at the definitions of fairness and how priority plays a role. The priorities that you assign to incoming requests may depend on a variety of different properties. So they may have to do with some intrinsic attributes of the tasks that are being performed, so class and instance variables. It may be some explicit representation of task priority, cost, price, or urgency. So in the request itself, you may say, I want this to be at a higher priority. It can be the number of tasks that are waiting for some condition may also play a role. So if there's a large number waiting, then in the interest of fairness, you want to give them some higher priority. The time at which the task is added to the queue may also be important, so you don't want tasks to wait too long to be able to get in, so that may bump up their priority. There may be different kinds of fairness guarantees. We'll see that in a moment. The expected length or duration of the task may also be important. So for example, you might want to give priority to very short, rapid tasks, and tasks that take a long time, you might want them to wait until the system is more idle. It may also be the desired completion time of each task. So this has to do with the explicit priority that you may be setting. You should say, I want this done by such and such a time. There may also be dependencies amongst the task. So then you want to have certain tasks which are done before others. And this is not even a complete list, so there may be lots of other properties that you might be interested in setting priority, current time, number of tasks, and so on, and so on. Now, there are different ways of defining fairness. So we have an intrinsic understanding of what it means to be fair, but there are actually different ways that this can be defined, both mathematically and also operationally. So on the mathematical side, there are notions of weak and strong fairness. So weak fairness means that there's a lot of onus being put on the requester of a service. So if the process continuously makes the request, eventually it'll be granted. So this blocks that process. So think of a dog begging for food. If it waits there long enough, it'll eventually get its food. Strong fairness is stronger in the sense that the guarantee that is offered must be stronger. So here the process has to do less. If a process makes a request infinitely often, but it doesn't have to block, eventually it will be granted. So think of a cat who checks if there's food in its bowl and there's none, it comes back later, checks again, eventually it will find some food. But unlike the dog, it doesn't have to sit there constantly waiting. So that's why this notion of fairness is stronger. But as you can see, both of these notions of fairness, weak and strong fairness, are very mathematical and abstract. So it's not immediately obvious how you would implement them. On the other hand, we have a couple of other notions of fairness which have a much more clear operational sense. So first of all, there's linear weighting. If a process makes a request, then it will be granted before any other process is granted the request more than once. So there's some bookkeeping is involved. This is like buying tickets for a concert or whatever, where you can only buy one ticket. So you put one per customer tickets. And then only once that ticket is consumed can you buy another ticket. So you can't buy all the tickets that there are and starve out some other clients. And then operationally, the clearest and the simplest one is the notion of a queue, first in, first out. If a process makes a request, it'll be granted before that of any other process making another request. So this is like standing in a queue at the post office or for a cashier at a bank or at a supermarket. In order to implement any kind of approach, you have to layer this policy over the underlying service mechanisms. So that means you need to intercept the calls, decide what your policy allows you to do, how you're going to implement fairness, and then pass on to the actual service underneath. So there are a number of ways of doing this. So the simplest, which is one that we've seen before, the notion of a relay, is a pass-through. So the host then has a set of immutable references to helper objects and simply relays all the messages to them within unsynchronized methods. So think, for example, of a web server with a farm of actual machines behind it that can service requests. So all the host does is it gets a request and it says, okay, I send it to this helper. It'll take care of the rest. Next is the notion of lock splitting. So here, instead of splitting the class, you split the synchronization locks associated with subsets of the state. As an example, think of a database. So a database has lots and lots of records, and when you make a database transaction, you don't lock the whole database. You simply lock the individual records that need to be touched on a particular transaction. So you have much finer grained locks. So the lock is not at the level of the whole object, but at the individual parts. And these are associated with subsets of the state. There, as an example, there's concurrent hash map. That's a Java class, and it uses an array of 16 separate locks, each of which guards one of 16 hash buckets. So it uses this internal lock splitting in order to offer better liveness guarantees. And then the approach that we'll have a closer look at today is that of before and after methods. So here, the service is split up into 3 parts. You have a before method and an after method. Each of these are responsible for maintaining the instrumentation and implementing the fairness policy and the concurrent access policy. And in between them is the non-public method, which actually performs the service. So all the synchronization and the policy for managing concurrency and concurrent accesses is done in before and after methods, and the rest is done inside the protected or private methods. So far this sounds very abstract. Now let's have a look at a concrete example, that of readers and writers. So this is a classical class of problems which illustrates very well the issue of concurrent accesses. So readers and writers, it's a family of concurrency control designs where we distinguish between 2 types of clients. Readers request only services that access the state of the object but do not modify it, and writers are clients which access methods that actually perform a change of the state. Now, what's important to understand here is that readers don't conflict with readers. So I can have multiple readers reading at the same time because they're not modifying anything. There's no conflict between them. The only conflict is with writers. A reader and a writer conflict because the writer may be changing what the reader is reading and lead to an inconsistent state. And more so, writers conflict with writers. So that means that anytime a writer is involved, the writer needs exclusive access. But whenever only readers are involved, they can enter the object concurrently. Here we see an example, a very simple example. We have 2 readers here. We have the host, which is the object that's providing the services, and we have 2 writers. First of all, one reader comes in and accesses the host with a read action, which is running for some length of time. And a second reader comes along and makes a request, and it can proceed in parallel. So these 2 tasks can overlap here. That's all fine. If while the readers are reading, a writer comes along and makes a write request, it has to wait. It cannot get in because it will conflict with the readers. At some point, both reader 1 and reader 2 leave the host, and at that point, and only then, can the writer come in. The writer, however, conflicts with other writers. So if there was at the same time as writer 1, writer 2 that made a write request, one of the 2 will get in and the second one will have to wait. Furthermore, if there's a further read request while a writer is active here, then that reader will also have to wait. So writers have exclusive access, readers do not. Finally, once both of the writers are out of the host, the second reader can come back in again. Before we dive into how this can actually be implemented in Java, let's try and understand a little bit better the safety and liveness properties of interest. Here we're going to model with FSP and the readers and the writers, and what we're particularly interested in is who gets access. So what does a reader do? It acquires a read access, it examines or reads the host object, eventually it releases its read, and it loops around. What we're interested in is the acquire read and release read actions. We don't care about the examination. So here we're excluding that from our consideration. It's important to model that the reader does something between acquiring and releasing the read, but from the perspective of our analysis of safety and liveness properties, we extract it. So it gets mapped to a so-called tau action. Same thing with the writer. The writers acquire and release, and in between they may modify the object, but we are not so much interested in what happens there within the modification action. So we have defined now our readers and writers. We have to control their access to the host. So here's a possible readers-writers protocol. There are many different ones that we can come up with, which will have different properties from the perspective of safety and liveness, and particularly fairness. But let's keep it as simple as possible. So the policy needs to keep track of two pieces of information. So this is the instrumentation that has to be performed. We want to know how many readers are in the object, have access to the object, and we want to know whether or not there is a writer. We could also keep track of the number, but it's of interest is only whether it's 0 or 1. So readers, we have a maximum of 2 readers and 2 writers to keep things simple. So the first variable here, a parameter I should say, is takes the value 0, 1, or 2, and the writing parameter has the values true or false. Recall that this is macro expanded, so this is a compact way of writing an FSP process, a finite state process, that will express the entire protocol. We essentially have 6 cases to consider, a maximum of 6 cases. So when the readers are 0, 1, or 2, and when the writers are whether there is or is not a writer in the object. Obviously, some combinations of this are impossible. So particularly, we want to avoid the situation. It should not be possible for it to be non-zero readers and also a writer in at the same time. So when is it possible to acquire a read? Anytime there is no writer currently active. And what does this do? This updates us to a new state, so we update our instrumentation state, so there's one more reader and the writing variable stays the way it was. A release read can be performed at any time, from the perspective here of the definition of the protocol, and that simply decreases the number of readers. When can we acquire a write? Well, certainly there should be no active readers and no writers. As a consequence, readers must be 0 and writing should be false. And this then updates. The number of readers does not change, but the writing variable becomes true. Release write can be formed at any time. Well, it can only be done after acquiring a write, and this just sets the writing parameter back to false. Now let's consider the safety properties that we want to guarantee. Recall we can have any number of readers in, but no writers, or at most 1 writer. So we have to keep track of this state. So abstractly, what this means is that initially we're in a the safe reader-writers property initially allows us to either acquire a read or acquire a write. If we acquire a read, then we go into the reading state. And initially we will be reading, we will have 1 reader in here. The reading process, again, this is macro expanded. There can be any number of, any non-zero number of readers here. And as long as we're in this state, we can acquire further reads. So further readers can join. Furthermore, if I is greater than 1, then we can release read and we decrement the number of readers. If, on the other hand, the number of readers is exactly equal to 1 and we release the read, then we go back here, back to the safe read-write state. From the safe read-write state, we could also acquire a write, and then we enter the writing state. In the writing state, the only thing that's possible is release write, and then we go back to our safe state. That's everything. So these are the safe interactions. Remember that the safety property is a transparent process. It specifies exactly what should be allowed. We don't have to explicitly state what's not allowed. Everything else is considered to be an error. So it doesn't say how this works, but it says what is allowed. And it's also transparent. If we compose this, there should be no impact on the underlying process. So here we have in FSP our specification. We have our reader and writer objects. We have our read-write lock, which specifies how, under what circumstances we can acquire and release a read and write access. And here is our safety property. It says that we want to allow reading or writing from the initial state, and then when we're in the reading state, we can acquire more readers until there are no readers left, and then we can go into a writing state. But from a writing state, we can only release the write. If we now select this process and compile it, have a look at it, here's the read-write lock object property. And it states, as we expect, yes, that initially we can acquire a read, we can acquire more reads, and eventually we release read, or we can acquire a write and release a write. If in the initial state we release a read, this is an error and should not be allowed. Furthermore, if we've acquired a write and we then want to, for example, release a read, this should also be an error and should not be allowed. But our underlying implementation should not allow this in any case. Here's the safe read-write specification, and it says that we can acquire a read, acquire more reads, then release reads, and then come back to our safe state. But if any other action is performed that doesn't make sense, this is going to be an error. Now, if we can compose these two, then we see that we have exactly this composition. This is our original read-write lock object, which allows us to acquire reads, multiple acquire reads, but acquire only a single write. Anything else is considered to be an error. Now, if we compose the readers and writers with the protocol and check for safety violations, we'll see that actually everything works fine. Here's our readers-writers specification. We have 2 readers and 2 writers and composed with a read-write lock. We compose them, and we can also check for safety properties, and there are no deadlocks or errors. When we compose this and have a look at the end result, it looks very healthy. We can initially acquire a read and get multiple readers in here. Eventually we release our read access, and then one writer or another writer can come in. So we can see that there are no terminal states here, and as a consequence it's always possible, there's a weak form of fairness, that eventually further readers or further writers can get access to the resource. We also would like to specify liveness properties, and this is precisely what we saw. So we want to ensure that it's always possible for a reader to eventually acquire read access and for a writer to eventually acquire write access. Assuming that we have fair choice, then we should have no liveness problems. Here, if we check for progress, no progress violations are detected. So everything is well. However, if we change slightly the definition of our protocol, then we may get problems. Suppose we consider, there are lots and lots of writers, lots and lots of readers, not too many writers. What we don't want is for readers to starve out. So let's say that as long as only readers are in, we'll allow further readers to come in, and we'll give them priority over waiting writers. Then we can actually specify this. We can actually specify this in LTSA using the priority operator that says, please give priority to readers over writers. As a consequence, we may actually starve out the writers. Here's our priority version of readers and writers, read-write progress. Let's select that one. And if we compile it, actually if we'll check for progress properties, it says this sequence of actions can lead us to a problem. In particular, if we have the two readers that continually make requests, then we can get into a deadlock state, a terminal state. We can see this here. Here we have the situation. The writer 1 gets in, it comes back out. Writer 2 can come in, get back out. If reader 1 gets in, then reader 1 performs some action, but at that point then reader 2 might grab a lock as well. So even if reader 1 releases its lock, reader 2 is in there. So there's always either reader 1 or reader 2 in here. Notice that this block of states here is a terminal set. We don't actually get out of there. Assuming that reader 1 and reader 2 always have priority and they're always asking to get in, which is how we've specified it, then writer 1 and writer 2 can never get in here. So this will violate our fairness and particularly our liveness property. And this is what we see here in a minimized version. Here, if we ask for minimization to get rid of the tau actions, we will see this this simpler version of the same diagram. So here we can see much more clearly, because it's not cluttered with the tau actions. Writer 1 acquires releases, writer 2 acquires releases, but if either reader 1 or reader 2 get in, then the other reader can grab the lock and we loop around here forever because they have priority and they're always asking for access. Now let's have a closer look at the different kinds of policies that can be defined, starting with the simplest one. So here are some of the considerations that we have to take into account when we're defining a readers or writers policy. So one question is, can new readers join already active readers even if there's a writer waiting? If the case is yes, writers may starve. That's bad for fairness and bad for liveness. If not, however, then the throughput of the readers decreases. So what do we want? So maybe we need to consider whether there is a writer waiting or not. So if there are writers waiting, then we may have to temper our policy. So how many writers are waiting, how long are they waiting, and so on. If both readers and writers are waiting for a writer to finish, which one should you let in first? Should it be readers? Should it be writers? First come, first serve. That's simple. Always queues are very simple. Should it be random? Same thing after a reader finishes. What do you do? How do you decide to proceed? Do you keep things simple with a queue? That's always the easiest thing to do. And what we haven't considered is what happens if a reader is performing some actions and suddenly decides, oh, well, actually, I just thought I was going to read, but really I want to perform a transaction now. I want to update the state. Can I upgrade to a writer, or do I have to leave and then come back as a writer? So upgrade policies might also be interesting. So to keep things simple, here's a typical set of choices. We block incoming readers if there are waiting writers. So keep track of a queue of writers trying to get in. You randomly choose amongst the incoming threads. That is, let the scheduler choose. And the scheduler typically is going to be keeping a track of a queue of waiting processes. And keep things simple to avoid having any upgrade mechanisms. So if you do want to become a writer, then you have to give up your read access and afterwards acquire the write access. The simplest way of implementing such a policy is use before and after methods, which we'll see now. So in order to implement the policy, we need some instrumentation. That is, we need to implement some variables that keep track of our state. So in our before and after methods, we will be asking questions about what is the state of the readers and writers in the system. So here's information that we might want to keep track of. How many active readers are there currently? Could be 0 or more. How many active writers? Before in FSP, we just modeled that as a Boolean because it should always be 0 or 1, but we can also model it as a number. In addition, for some additional fairness, we want to know how many waiting readers and waiting writers are there. So if I have a lot of readers in the host and a writer comes along, well, how many writers are there? And if a new reader comes along, if there are no waiting writers, well, I'll just allow that new reader in. If not, then I have a decision to be made. Then we have do read and do write. Those are the actions that are performed between the before and after methods. So this is what our services are going to typically look like. Here's the public read service, and the public read service is broken up into a before method, in this case before read, an actual method to perform the action, and an after read. Notice that the read method is not synchronized. Before read and after read will typically be synchronized because they have to decide whether we gain access or not. And once before read succeeds, then we can perform the do read action in unsynchronized code. The write method looks pretty much the same. The details, of course, are different. The logic of before read and the logic of before write are rather different because we want to distinguish between readers and writers. Here then is a very simple form of a readers-writers policy with our before and after read methods implemented here. We have to both maintain the abstract state, so our instrumentation variables, and also use them in order to implement the guard and the notification. So the before read method is going to be the guard, and the after read method will perform our notification. And both of them are maintaining the state. So before read means that there's a client, a thread, trying to get in and obtain read access. As a consequence, we increment the waiting readers. Then we call another method that checks whether we want to allow the reader in or not. So for example, we check that there are no writers, no active writers. And if there are active readers, then we then that doesn't matter. We may also want to check whether there are any waiting writers. So if there are waiting writers, there may not be any currently writers in, but if there are waiting writers, we may also want to delay access to the reader. That depends on the choice of the policy that we would like to implement. So with this design, we can easily change the logic of the actual guards. In other words, if the reader is allowed to get in, then we will pass this guard. If not, we wait Here we're in a synchronized method, so we give up the lock to the object, and we're waiting for some other thread to change the conditions of these instrumentation variables so that we can then check again whether a reader is allowed to get in. Once we know that we're in, notice we're still holding the synchronization lock here, then we decrement the number of waiting readers because we're no longer waiting. Now we're going to become an active reader. So the maintenance of the state is dead simple. We just increment and decrement waiting readers and active readers. After this method, as we saw before, we do the read, and once the read method is done in unsynchronized code, then we go to the synchronized after read method. We decrement active readers because we're done, and because the state has changed and we're done, we're going to be giving up control of the synchronized lock. Then we want to notify all the waiting threads so that they can check whether they're allowed to proceed, whether they're readers or writers. Here's one possible implementation of a policy for allow reader. Obviously, we want active writers to be 0. If there's an active writer, we must wait. We cannot get in. But we might also want to give some priority. If there are waiting writers, we want to be polite and let them in. Conversely, if a writer is trying to get in and sees that there are waiting readers, perhaps it wants to be polite as well. But we have to make sure that one or the other gets in. So we can't have a situation where everybody is deferring to everybody else and then nobody gets in. So you have to reason quite carefully about this. I strongly suggest you, as an exercise for yourself, without looking at the sample code, see how you would define suitable before and after methods for the writers that don't lead to other liveness problems. Let's have a look at our implementation, and we'll have a demo here where the readers and writers are simply printing out open and close parentheses and open and close square brackets to show them when they are gaining and releasing access. So here we are in the sample code. Here's our readers writer state tracking class, and we have our abstract methods for doing our read and write actions, and the policy is defined as follows. Before read, we want to allow a reader in if there are no waiting writers and no active writers. And we similarly have defined our allow writer method, which I'm not going to show you so that you can think about it yourself. And here we have a demo which extends the abstract class by implementing the do read and do write methods. And we're going to create a certain number of readers and writers to execute in parallel. So we have 2 readers and 2 writers, and they're each going to loop and print open and close parentheses for the readers and open and close square brackets for the writers. In addition, in order to see if we can provoke a raise condition, we'll do a thread.yield in the middle to simulate, to provoke some possible interleaving. And then we can check and make sure that there are no violations of the readers writers policy. Now, if we run this guy, you can see quite clearly that the readers may overlap, but they do not overlap with writers. Writers have mutually exclusive access. Never do we have 2 writers overlapping, but readers may overlap in multiple ways. And we can run this as many times as you like, and you'll find that there are never any violations of this underlying policy. In this last part, we're going to have a look at a rather different approach to ensuring safety. And instead of using locks as we had up until this point, which are basically a pessimistic mechanism, a lock says Now I want mutually exclusive access so nobody can butt in. And then when I'm done, I release the lock. And in order to get more liveness, we have all sorts of tricks like we've seen in today and in other lectures to increase the amount of available concurrency. With optimistic methods, on the other hand, what we will do is instead of using locking, we will keep a backup of our state. We'll assume there's not going to be any interference, but before we commit our changes, we'll check. And if there is a violation, then we'll be prepared to roll back. This is exactly what's done in transactional systems, where we either cannot lock or cannot afford to lock, and we want to be as optimistic as possible. We check for possible violations of exclusive access. So with optimistic methods, they attempt actions without synchronization, and they roll back the state in case a collision has been detected. When they roll back, they either can throw a failure exception or possibly retry. You can apply this design pattern if and only if you can tolerate failure or retries. If not, then you should go back to the standard solution using guarded methods. You should also be able to cope with live lock. So if I have a thread that's optimistically performs a method, is forced to roll back and tries again, we want to be sure that it doesn't starve due to live lock. So live lock is like deadlock in that you don't make any progress, but with deadlock you're just blocked. With live lock you continue or you're continually doing stuff, it's just not useful stuff. So with live lock you're essentially busy waiting and doing making useless attempts to move forward. It should also be possible to undo action. So the rollback must be possible. And you can undo these actions before the failure checks. So you can either have a rollback and recovery, so you can undo the effects of each performed actions. Furthermore, if there's communication with the other objects, you have to be able to undo those actions as well. For example, by sending anti-messages, so a negative message. Once you've done something, you can say, oh, please undo that. Another approach is to have a provisional action. So you pretend to act, and then only once you have the okay, then you actually commit. So for example, you can do all your computation in a scratch space, and once you confirm that there's no interference, then you commit in a symbol atomic action the update. In the design steps, you have to make sure that all the mutable state can be encapsulated, so you can track it as a unit. And this can be done, for example, with the help of an immutable helper class that holds the values of all the instance variables. Or you can define a special representation class, which is mutable, and maybe include a version number or a timestamp. Or you can embed all the instance variables and a version number in the host class and define a commit method that takes as an argument all the assumed values and the new values, so you can compare. Have the values been changed while I was performing my action? And then, of course, you need to maintain a serialized copy of the object state. Is another possibility. So serialized copy means that it can be streamed out into, for example, into a file. And you can have various combinations of these approaches. Now, the key thing is, so you have your optimistic method, you're performing your actions, but then you have a certain point where you are ready to commit. But before you commit, you have to check if there's been a conflict. So you need an operation that detects whether there's been a version conflict. So for example, comparing the timestamp or comparing the values that you assume that the state that the object was in, or any kind of combination. It could be version number, it could be timestamp, it could be the actual values. So here's a very simple version So this is just a sketch of the code. We'll see a concrete example in a moment. So it's a commit method, and the commit method is synchronized. Here's the state that we assume that we were in, and this is the state that we want to move to. But we want to make sure that nobody else got in and changed the state underneath us. So if the current state, our current state, is different from our assumed state, that meant some other thread got in underneath us and changed the state while we were busy working. If that happens, if we fail, then we do not commit. So this success tells us whether we succeed in committing or not. If it's okay, then we update the state. Notice this is in a synchronized method, so the state of the object now really gets updated. If we failed, then we simply return success false. Let's go back to our bounded counter. So here's an optimistic version of our bounded counter, and the bounded counter's state, recall, is the count value. So our methods for updating the bounded counter are not going to be synchronized, but only at the last step where we actually do the update and perform the commit do we check. So here, this is the previous value of the count value. This is the new value that we've computed. We check, is the count still the old value? That is, nobody else messed with us. And if so, then we do the update and return true. Else, we return false and we failed. And just for demo purposes, we're actually going to print out a message saying that the commit failed. Now, in the methods that actually do the actions, in unsynchronized code, we'll do our computation, and at the last step, we will check whether we can commit. If we commit, then everything is fine and we can continue executing. So if not commit, then we roll back. If we do succeed, then we continue to do other stuff. And if we fail, then we'll have to roll back or possibly try again or whatever. In our optimistic bounded counter here, here's our increment method. Notice the increment method is not synchronized. We have a loop here, and in the loop we'll check our value. We have to remember the previous value, sort of current value at this point, but it will be the previous value. We perform our computation. Actually, the only computation that we're going to do is compute the new value, and then we attempt to commit. So if the value is less than maximum and we can commit, then we break out and everything is fine. If we fail to commit, then, well, we had a problem and we'll have to try over again. So in this particular case, we have a thinly disguised busy wait because this is a for loop. But just to give other threads a chance, we're going to do a thread.yield. We could also do a short wait if you like. And then we loop back. Once again, grab the current value because it may have changed. This is unsynchronized code. We compute again, what the next value should be if the value is not at the maximum. Notice that if this fails, then we're still going to busy wait here. So if the value is already at the maximum value, then we cannot increment and we don't even try to commit a change. If we're not at the maximum, then we try and commit the update. And if that fails, we loop. Now, of course, you have to decide what to do if you fail. So if you could not commit your update, do you simply report an error? So you can throw an exception and tell the client, decide what to do. Or you can directly retry the action until it succeeds, but that could lead to live lock. You could also retry some bounded number of times or until you get a timeout, and then finally throw an exception, so you have a combination of these two approaches. Or finally, you can say, okay, this is not working, let's fall back to another approach. For example, we can call a fully synchronized inc method instead. You say, okay, being optimistic is not working, let's fall back to a pessimistic approach and we know that that will work. So this is also a viable solution. You want to ensure that there's progress in case of internal retries. So immediately retrying is probably not a good idea. You might want to wait a short time. Yielding can help, but that may only be effective if all threads have reasonable priorities and the scheduler is fair, and that's not guaranteed, and you might want to limit the number of retries to avoid a live lock. So it can get complicated in the worst case. But as I said, one of the things that you can do is have a bunch of fallback strategies, and in the worst case, fall back to a pessimistic approach, and that can be reasonable as well. Here's the bounded counter in IntelliJ. So it's another implementation of our abstract bounded counter. Notice that our inc and dec methods are not synchronized, and the only synchronized method is the commit method. And the commit method will check and see whether there's been a conflict. If there's no conflict, then it simply succeed. If it fails, then it will say commit failed, just for demo purposes, and we'll just loop around yielding periodically to see if we can eventually get in. Recall our test class where we have 100 incrementers and 100 decrementers, and we check in the end that we have no errors, so no violations of our class invariant, and that the value at the end after 100 increments and decrements is back down to 0. So we didn't lose anything. And here's our optimistic bounded counter, and let's run the test for this guy. Notice that by having lots and lots of threads which are banging on trying to access the same variable, we're violating in a sense the underlying assumption of optimistic methods. So you want to use an optimistic approach when you don't expect there's going to be a lot of contention. So for example, in a database system, when we have lots and lots of database records and lots of transactions, but the chance that two transactions want to access the same database record is very, very low, then an optimistic approach makes a lot of sense. And just when you're ready to commit the transaction, you check in case there was a conflict, then you roll back. But that's very rare. In this case, we constructed the test in the opposite way. We have 100 incrementers and 100 decrementers all trying to access the same bounded counter at the same time. So that's going to generate lots of conflicts. So here we have lots and lots of conflicts, but in the end, everything worked out. We got 0 errors, so no violations of our invariant, and the final result was what we expected. So the commits that failed were retried, and eventually they all succeeded. Okay, that's everything I wanted to show you this week. So thanks for your attention.